Good morning. Let me share my slide. We continue our discussion on this Bayesian decision theory or Bayesian decision making process, and we will consider another framework under this theory, which considers in general, it's a generalized framework of the decisions what you have taken. Earlier, you have considered only the decision as a um, as the class assignment problem. So kind of uh, action is every action is considered with respect to. I mean, the problem was posed that wherever the posterior probability is maximum, um, you assign for that particular type of class. Now, we consider here in a bit more generic framework that um, here the class assignment is an action. Every class assignment is an action. Or you can consider also any kind of decision process where uh, taking a decision means uh, you're uh, you're having an action there. Now, uh, when we are considering, so it is something like that. You are evaluating that what are the probable states from your current state, what are the probable states or from your current, I think the base condition, what are the possible states that you can arrive at, and then in that state, what are the possible actions you can take. And every action will have certain cost. So finally, your decision making would be to take that action which will have either if it is a loss, which will minimize the loss, or if it is a gain, then which will maximize the gain. So let us try to understand within this framework. Say, as I mentioned, that here we are considering class assignment is an action. And if we consider that ith class represented as Ci, if I assigning an input sample to that class, then I consider that's an say ith action, or which are we are denoting here by the symbol AI. And consider that um, loss due to AI if X belongs to CK. Uh, so, so we are considering that in this case loss in this fashion. Suppose uh, X is originally X is in your target function. X belongs to CK, right? In your target function, X belongs to CK. X should be mapped to the kth class, but no, you are taking an action where you are mapping X to ith class. So there is a loss associated with it, and we are denoting it as a like earlier. This loss was uniform for every class. Suppose there is a misclassification of a particular sample, we consider the loss or error is uniform, right? So we are just counting number of misclassifications. But in this case, we are also having some kind of weights of different assignment to different classes. So some classes may be quite similar to kth class, and maybe loss is less. In some classes which are very distinct, maybe loss will be more, something like that. So first thing what you should consider that if we take the ith action, that means you assign it to Ci, then what is the expected risk? So expected risk in the sense that you know that posterior probability distribution for every class. So again, that posterior probability becomes the probability of of your of the x belonging to that state. So expectation is, that is the probability distribution. See, over that probability distribution, what is the expected risk? So we can represent it in this form. Say, for the ith action, the expected risk is that you consider the probability of x for its belongingness to Ck. So what is posterior probability of Ck given x, and then the corresponding action Lik, loss Lik would be considered. So it is weighted average of Lik. As you understand that sum of posterior probabilities given an input should be equal to 1. So this is how it's, and also it's a probability, so we call it expected risk. So finally, your decision making would be done in this way, that you choose that action which will minimize this risk. Okay? So there are, suppose in this case, if you have n classes, you can have a set of n actions. Now for every action, if given an input data, you can compute this risk, and then you choose that action which will be minimal. Now that means you are, again, action means you are assigning x to that class here. So it is, you can see that ultimately, if a very special case where you keep all the losses uniform, all the misclassification losses uniform, and all the true classifications, correct classifications loss is 0. If you keep it in that way, then you will see that it is the same as what you did earlier, which means maximizations of posterior probability or map approach, by which we will be selecting an action. So that is what some of the cases we will be discussing, and that would also show that how generic is this framework, and those are the special cases. So you consider this particular loss function. For ith action, you see that if x belongs to, if the sample belongs to the class kth class, so if your I is k, that means your action is that you assign to that class also, then of course the loss will be 0. That is our intuition. And otherwise, it's a misclassification. So the loss is 1, which means it is uniform. So under this framework, if I compute this particular expectation of losses or risks, then you can just simplify this expression. You can see for every action, what is its expected loss. This expected loss will be, as you see that it is 0 for I equal to k. So you just sum all the posterior probabilities except the probability except the value at at a particular value at I, right? So if it is truly, if it truly belongs to that class, right? So then this is equal to 1 minus probability of Ci given x, right? So that is the posterior of that. So this is the same as this, because sum, as I told you, sum of posterior equal to 1. So you have excluded only the, according to this loss function, you have excluded the posterior of ith class. So this function is this. So it means that if you are minimizing this risk, then which means over all I, you have to basically maximize the posterior probability over all I. So again, it is the same Bayesian inference this we can see. So let us consider a bit more general framework where we consider a certain situation where it would be, that means your posterior should be of posterior probability itself should be of sufficient strength. If it is not of sufficient strength, then it's a doubtful case, and you do not assign. That means you are additionally also you are including one additional action, which means no assignment. So it is not that you have to always assign to a class. You can also simply default. You can say no assignment. So we consider that let there be an additional k+1 action for rejection. Rejection means the sample is not assigned to any class. So in this case, we define the loss function in this fashion that you see that I mean the lambda is the kind of risk you are taking if you are not assigning a sample. Now lambda should be less than 1, right? Lambda should be less than 1 because you are not taking any decisions. It's a doubtful case, and so the loss is not at par with misclassification. So that is the kind of intuitive understanding. And otherwise, the framework remains the same. If there is a class assignment, if there is a misclassification, the loss is 1, and otherwise, for true classification, loss would be 0. So once again, we can compute to the same expected, and there we can see that same we can, for I not equal to k+1, you have the same value. But whenever you consider the k+1th action, then you have to choose basically the lambda. That is the loss. Lik becomes lambda for k+1th action, and irrespective of any class assignment, this lambda should be there, right? So which means your risk is lambda. That is just not theoretically. You can also show it, which is also from our intuitive sense we understand that no assignment means the risk is lambda. So now you understand that the problem of minimization becomes that it is maximization of the posterior, but posterior should be at least greater than 1 minus lambda, right? This posterior should be otherwise, if the lambda is minimum, then then whatever value of posterior is there, then you have to choose always lambda. So your decision would be something like this, that you should choose that particular action. If you choose AI, that means you can assign a class Ci to that X if you find that your posterior is maximum in that class, and also the strength of posterior is greater than 1 minus lambda. So now you understand that in this kind of decision making, we are actually computing the posterior probability. It is not just proportional to posterior, what you did earlier. So here we have to compute the posterior probability, and then only we can take this kind of decisions. And otherwise, no, we have to reject, or that means no class assignment. I think it is the same thing. So just to note down that, as I mentioned, the meaningful if lambda should be between 0 to 1, and if lambda is 0, which means you are always rejecting. That means you are not doing any class assignment. That's the extreme case. And if lambda is 1, which means you are always accepting the class. Some assignment will be there. Now, we discussed with respect to the risk loss function, but it can be also generalized with respect to the utility theory. It is the same framework, so I'm not going to elaborate here, because as you can see, instead of minimization of risk, here we maximization of the utility. Again, once again, you are doing the same way. You are computing the expectation. So far, no, this is one kind of, as I mentioned, that we have discussed about the Bayesian decision-making process, Bayesian theory, and then Bayesian inference mechanism. But there are other another interesting aspect I would like to also discuss here, I mean, which is not exactly the application of Bayes' theorem, or which is not exactly the Bayesian inference, if we say. But it is, you can see that under the similar probabilistic framework, we can also do the rule mining, and particularly we can mine the association rules. So that I would like to discuss as a continuation of this particular topic. Now, let us understand what is meant by this association rule. So it is as simple as an implication. That means if X occurs, then Y happens, right? So once again, like a rule, no? Like you have the correspondent antecedent part and causal part. So it is there. It is so in that way, association is also depicting a rule, but it's a kind of context by which these associations are more understood. For example, a basket analysis for dependency on procurement of items X and Y. So you have many a times now you see in online shopping when you buy something, so there are certain recommendations of other products. Now those are those recommendations, they come from this kind of analysis. So I mean there are a lot of data of past procurements by which the system finds out that what is the probability that if you buy X, then also you will buy Y. So this is a kind of way. If it is quite high, then we recommend it, and we'll be basically discussing the computational as a computational problem how to find out this kind of associations when you have this data of occurrences of X and Y over number of events. So there are three useful measures which are in this context, which are used when we choose a particular association. Actually, the approach is a bit, if I say, you can say it's a combinatorial problem. Suppose you have a set of attributes, say X and Y, they are representing attributes, right? They are random variables or attributes. Now you have a set of attributes. So now, out of that set, you are finding out certain subset is, implying, or there exists an association between some subset of that attribute set to another subset, right? So you have to find out that. So one way you can consider, because you have the data, one way you can consider that, okay, let us consider all possible type of combinations, though as you understand that is prohibitively computationally expensive, and you cannot really do that. But from the understanding point of view, let us consider you are being allowed to do that. So randomly choose any combinations, right? Any kind of subset, and then you find out from your data sets whether there is an association. Now, for that, whether there is an association, what you can do, you can measure, you can use certain measures. That means you observe how many times they are occurring jointly, etc., and what are the fraction of times they are occurring, etc., etc. So there could be different ways you can approach this particular problem for establishing, if I give you two subsets, whether there exists an association or not. So that problem is easier to handle than I said that find out which two subsets are associated. Right? So I give you two subsets and I ask you that whether they are associated. So you can see that it has that NP complete problems flavor. So it is really NP-hard problem. Anyway, so we'll be considering this. We'll be first discussing those measures. Now, one of the measure is called support of these two attributes. See, I'm saying X and Y as if single attributes, but they could be also set of attributes. So X is a set of attributes and Y is a set of attributes, and they are disjoint, right? So, but let us, for the sake of simplicity, let us understand they are single attributes, because the generalization is very simple. It's very direct extension what we discuss here. So, so joint occurrence of X and Y, that is what we would be considering. Now, this is an important measure. Sometimes, X and Y may be occurring very sparsely, rarely, and you might see in one or two cases, yes, these two samples are there. Now, there, if we consider other measures later on, we'll see those, we call them evidences. Now, those evidence of joint occurrence could be with respect to the fractional times X occurs or Y occurs, that would be quite high. But actually, the occurrences of these two are may not be so high. So that's why the support measure needs to be. This is a kind of strength, and support should be bit. This probability should be significant enough, or should be high. So naturally, the definition is like the way we define any joint probability of two random variables. That means if I considered the number of events, total number of events, then how many times x and y occurs together, right? So that is what here is expressed. We are giving all these definitions in the context of basket analysis. So you can generalize these definitions in a more abstract form, right? So this is the joint probability of x and y, and we are calling this measure as the support of x and y. Whereas confidence of this rule, that means x implying y, is basically you are measuring probability of y given x. So as you see that this is the kind of I should say conditional probabilities which is coming into the picture, and some relationships with that probabilistic approach of Bayesian inference. So which means from the definitions you can see itself that how many times x has occurred, out of which how many times x and y both occurred, right? So that is what you are expressing by this probability of y given x. So this is the definitions here with respect to this basket analysis, that number of customers, they bought x and y both, and number of customers of x only. The third measure is called lift of x and y. Now you see that I have just given it in the abstract form, that you see that it's a ratio of two quantities. In the numerator is joint probability of x and y, and in the denominator is you have the product of probabilities of x and probability of y. Or you can also apply the Bayes theorem, and you can see that you can express it in this form: probability of y given x divided by probability of y, as if the confidence per occurrences of y. Or you can also write, which is not mentioned here. That's why I told that this causal relationship is very causal relationship is not really, you should not consider them as a causal when you are using this conditional probability, because you can also write it as you see that probability of x given y divided by probability of x. So that also you can write. So, but anyway, with respect to this implications point of view, we interpret this definition in this fashion. So can anyone tell me that what is this is trying to measure, this lift, what it is trying to measure? Is there anyone who can answer? You have some idea that what lift is actually measuring? Okay. I'm not getting any answer, probably. Maybe you're not listening much. Yeah, somebody is trying to say, am I missing? Say, Alka Ranjan, are you?
Same like.
Yeah, please tell me. I was not. Am I?
Sir, independence of x and y.
Yeah. It is trying to measure the independence, whether x and y are independent. So if it is independent, what is the value you should expect?
1.
Yes, the value should be 1. So if they are independent, means no, there is no association. So independence actually stresses that they are not associated. So that's why the value should be deviated from 1, actually the measure should be high, more than 1. If it is less than 1, it is less likely that there is an association. That is also considered. So just these are the implications, that confidence indicates strength of the rule should be very high, and it should be significantly higher than probability of y. That is what is the confidence. Support shows statistical significance, so should be of considerable numbers, right? So insignificant support with high confidence, meaningless. That's what I mentioned. And for independent x and y, lift is close to 1. So ratio other than close to 1 shows dependency. But however, if lift is greater than your y, then most likely x makes y. So as I mentioned that causal relationships cannot be ensured, but if lift is higher, lift is may indicate this causal relationship. That is what it is meaning. Otherwise, no, they are associated. If it is also less than 1, much less than 1, they are associated. But you may not say this implication rules there. So these are the 3 measures that you can judiciously use to decide that whether a subset or whether a set of attributes X implying another set of attribute Y. So that implication rules. Okay, but as I said that this is combinatorially explosive, because if I give you these 2 subsets X and Y, then you can compute this very easily, because this measures empirically you can compute over the data sets. You can use that, or some numerical methods you can use to compute all these probabilities, and then compute these measures and apply these heuristics, right? If you find confidence is high, if you find support is high, if you find lift is more than 1, then you can decide all 3s are indicating that probably there is association, and you can check that. But no, there are certain issues also, and the combinations are also important. So one of the thing is that, as I said, that your attribute sets could be your attribute set could be it could be a set of attributes. Particularly in your left hand side, it's a joint occurrence of all these attributes. So in the right hand side, in the consequent part, you can make it disjoint operations. But the left hand side operation is very important, because they are different. If I say xz implying y, naturally x will also imply y and z will also imply y. But no, occurrence of xz implying y is more stringent. Yeah, more stringent. It's not naturally, sorry. Xz needs to be considered there instead of that. So it's possible to generalize association among more than 2 variables. So there are 2 steps. One step is that so you use certain kind of greedy heuristics while finding out possible candidates. And first thing what you do, that since you require that your support should be high, so rather you would concentrate on more frequent item sets. So you choose those subset of attribute, that subset of attribute which consists of the which consists of those values which are occurring more often. So actually, I was talking about attribute. It is basically the values of attributes. Those are here associated. So that you have to consider here. So those which have enough support, and converting them to rules with enough confidence. So by splitting the items into 2, as items in the antecedent and items are be considered. So you consider the frequent item sets, and then that set you split them. That set you split them. That also you can do gradually. You can have an ordering of its occurrences, and you can slowly build up the rules. That means first you try to make the consequent part only say the antecedent part, because antecedent you will be composing and consequence will be checking one by one. So in the antecedent part, you are taking certain subset with a single item, for example. and you just find out that which are having enough support and or rather evidences, and then you shift one of the consequent part to that part. So let me give you this algorithm. So the step one is that this algorithm is called a priori algorithm, and it finds the frequent item sets, that is those which have enough support. So which means you start searching for combinations with lower cardinalities, say with one item, and then you find out two items like this, and the remove supersets in the combinations which are not in the list of lower cardinality sets, right? So you can remove those combinations. So if X is not frequent, so do not search for any combination with X. That means it says that now when you are searching the combination of attributes, they are consisting of those frequent items only, and they are consisting of those sets which are frequently occurring, right? So this is what it is considering, and it requires n plus 1 passes for searching largest n item set together. So this is the kind of first set, and then with those item sets, you convert them as a rule, as I said, which means you have identified the joint occurrences of those items. Now among them, whether there is any implications among them, there are two partitions or two subsets, whether there is any implications. That is what is your observation. That is the step two. So in step one, you are collecting those attributes or the values of those attributes, if I say, and in the step two, you will be basically splitting them into two as items in the antecedent and items in the consequent. So here also you grow the antecedent part from single item to a multiple item. So for every item set, as you said, split, keeping all but one in antecedent and one item in okay, sorry. So in the antecedent part, you are taking the whole thing. That is more harder constraint. So if you don't get it, then you reduce it for the less number of items. So for k item sets, k minus 1 items in antecedent and 1 item in consequent, and remove those rules which fail the test of confidence. So it is basically the evidences it is talking about, and also you can use lit here also. In every pass, reduce antecedent part and increase the consequent part. So in this way, you are iterating, and finally, where you get the rules with larger consequent part. So those are the rules that you will be using. I think this algorithm, yeah. So you can get the details of this algorithm in this reference, right? So it was proposed in 1996. You can read also Alperin's book where this is discussed. So just to summarize this particular topic on association rule mining of association rule mining. So as I was mentioning, that association again does not mean that there is a causal relationships. So that you should note down. And there may be hidden variables acting in the process which are not identified, which means that you are only operating with what is visible to you. Now, some of them are related with some hidden variable, and those dependencies are not expressed, so they may not be reflected in your data sets. Say for example, we have association among diapers, baby food, and milk. That may be established, but their hidden variable is something like baby at home, right? That variable is not reflected here. Anyway, so with this we have more or less discussed about these different topics under this Bayesian inference scheme, inference mechanism, and I will be just summarizing them. In fact, this topic will continue because we will also consider the other approaches. Particularly, we have so far discussed mostly on discrete variables, discrete random variables, and using them we have shown some examples of estimation of these likelihoods or posteriors or priors. So we considered that. But in the continuous random variable, those estimations are quite different. And in an arbitrarily large data also, we have a different kinds of estimation techniques. Particularly, there are two approaches. One is, say, parametric approach and non-parametric approach, or instance-based approach. So those we will be discussing next. So just to summarize this particular topic, whatever we have discussed under this topic, that as you see that the Bayesian inference is means actually what you are with respect to the class assignment problem, you are computing the posterior probability of class given X. So we are computing these posterior probabilities. And the map approach you are using, that means the assignment, the class which has the maximum posterior probability, you assign the sample to that. So that is the essence of Bayesian inference. If you say Bayesian inference classically, this is what it means. Though there are many variations of similar kind of inference things, which we do not exactly call Bayesian inference, like maximum likelihood inference I mentioned. So also we consider the framework. Yes, any question?
Examination. So you need to work to learn this particular.
I'm not getting your question. Please, can you tell me once again?
Come sustainable environmental solutions, then any environmental engineering is the best we are going to discuss and industry-oriented subjects, including air and noise fundamentals of control engineering.
Is there any question?
And chemical treatment of wastewater, biological.
No, I sorry. I think that's it. Yeah. I hope that there is no question. No? Okay, so you can say that no. Decision may be taken by modeling risk or utility of any action that we have discussed. Then classification rules can be set under the framework of discriminant functions. And Bayesian inference is useful in establishing association among variables. I mean, that is not, I should say it's the same mechanism or similar framework. You are not exactly doing Bayesian inference, as I mentioned already, that you are not always computing the posterior probability there. You are not computing posterior probability. But what you are computing the probabilities with the probabilistic interpretation is that you are computing this support, confidence, and lift. And using them, you take a decision whether there exists any association between X and Y. So particularly the rules with high support and confidence and lift should not be around 1. So lift should be either greater than 1, significantly greater than 1, and say or significantly less than 1. So with this, let me stop here today because we'll start next topic and we'll start this topic in the next class itself. So if you have any questions, let me know. So any question? Okay, fine. So in that case, we'll meet again next week on Wednesday. Thank you very much.